This is the video on Boltzmann distribution. Here I'll try to answer the questions of why do you often see Boltzmann distribution for a system in thermal equilibrium. To answer this question, let me first say what do I mean by Boltzmann distribution. Now a system can have different energy state and this energy can be continuous or it can be discrete. Now the question is what is the probability of finding the system at some energy state E, and it is given by P of E, and if the system is in thermal equilibrium at some temperature T, then this P of E is proportional to this exponential function. Here Kb is the Boltzmann constant and T is the temperature, as I said. Now let me give some example. One example is the Maxwell-Boltzmann distribution. Now if the ideal gas molecules are kept in a box, then their velocities at some particular direction, here I have said this is the ith direction and it can be x, y and z direction. So this distribution for velocities will be given by this equation. Now for the ideal gas, there are no interaction among them and therefore they have only kinetic energy, which is given by half mvi square, and so the E is totally kinetic. And this pre-exponential factor is actually ensures that if we integrate this API with respect to VI, then we will get 1. Therefore, it is the normalization constant. Another example is the diffusion process of a Brownian particle or a colloids in a thermal bath at temperature T, and the particle is confined in a harmonic potential of this form. Here gamma is the stiffness of this potential, and for this system the distribution of displacement in some direction x is given by this equation. For colloids, if it is in overdamped case, then the change in kinetic energy can be ignored and therefore the total energy is solely potential energy, and therefore you can see this distribution is Boltzmannian. Now let me start with a microcanonical ensemble. It is a set of isolated system with some fixed energy. Here I consider a isolated system whose total energy is E and it is made up of many compartments. Here I have shown that this system is made up of n compartments and the compartments have energies E1, E2 and so on to En, and their sum is E, which is constant. Now there may be another configuration for which the total energy is constant E, but now the compartments have different energies. Here you can see the first compartment energy E1, second compartment E2 and so on, and for n compartment is En dash. Therefore this configuration and this configuration, they are different but they have the same energy. Now suppose there are such omega number of configuration with total energy E. If all the configuration has the energy E, then they are equally probable and the probability of observing a configuration phi is given by this delta function divided by the total number of configurations. This delta function, what does it mean? It means that it takes value 1 if this configuration has energy E, otherwise it gives 0. If we sum this delta function over all the configuration, then it will just give the total number of configuration, right? Now in the previous slide we have shown that the isolated system have the same energy but they may have different configuration and the number of configuration is omega E. Therefore, there is some entropy associated with such system and it is here denoted as S of E and it is given by this equation which is called the Boltzmann equation. Though the exact expression of this equation was not given by Boltzmann, but the very idea of relating omega E with the entropy was put forward by Boltzmann, and rightly so. It is accredited to Boltzmann, and is in fact this equation is engraved on his tombstone, and this relation is of great importance particularly for the isolated system to calculate the entropy, and we will apply this relation later. For now, let me consider an isolated system whose energy is capital E and it consists of two compartments. The first compartment has the energy E1 and the number of configuration is omega 1. The second compartment has energy E2 with total number of microstate omega 2, right? And these two compartments are in thermal equilibrium at some temperature capital T. Therefore, the total number of microstate associated with this isolated system is given by omega 1 multiplied by omega 2. Now, consider one change is the energy of this first compartment by a small amount so that the number of microstate for the first compartment change, so as the second compartment. Therefore, the total number of configuration for the whole system will also change. But we want to know how it will change. And from the basic principle of thermodynamics, we know the change for an isolated system occur in this direction where the entropy is maximized, or in other words, the system explores the maximum number of microstate, right? So mathematically speaking, the change of omega with respect to E1 or E2 should be 0. Okay. Now after doing some simple algebra, we can arrive at this relation, and you can see the left hand side of this equation correspond to first compartment, whereas the second it is depends only on E2, therefore it corresponds to the second compartment, and they are equal. And as I said before, the two compartments are in thermal equilibrium, therefore these two quantities must be related to temperature. And as this equation has the dimension of inverse of energy, therefore we can say that these two quantities actually just the 1 by kBT, and using Boltzmann equation we get that dou S by dou E is 1 by T, and in this way one can define the temperature. Now, like the previous case, let me consider another isolated system with total energy E, and it has the omega T number of microstate, and it is made of two compartments. One is the central part, which we call system, and another is reservoir. Reservoir exchange a small amount of energy epsilon with this central part, and for that this central part attains a conformation phi, and the epsilon is very small compared to the total energy. And therefore, the energy of the reservoir is E minus epsilon, and suppose there are omega subscript r number of reservoir configuration. Now, I want to know what is the probability of observing the configuration phi for the system, right? So it is actually the sum of all those configuration of this entire system for which the system has a conformation phi. Or in other words, we can say that the system should choose those configuration for which the reservoir has the energy E minus epsilon, right? And what is the probability of observing that the reservoir has E minus epsilon energy is given by the delta function divided by the total number of configuration for the whole system, right? And this delta function means that if the reservoir has E minus epsilon energy, then it picks value 1, otherwise it will be 0, right? That means the sum of our delta function gives the total number of configuration of the reservoir with energy E minus epsilon. Okay, so P of phi is the ratio of omega r to the omega t. Now here we can apply the Boltzmann equation for the reservoir, and then we can get the entropy for the reservoir with energy E minus epsilon, right? As epsilon is very small compared to capital E, we can Taylor expand entropy around the capital E, and we expand up to first order and neglect the higher orders. Therefore, we get this equation, and you can see this term we can again use the Boltzmann equation to get the number of configuration for the reservoir with energy E, right? And you can see this is nothing but the Boltzmann distribution with this factor, which of course is the normalization constant. So you can see the probability of having the configuration phi is pre-exponential factor with this exponential function, and this pre-exponential factor is the ratio of the number of configuration per reservoir and the entire system of energy E. And the capital G, called the partition function, is the summation of this exponential function. And the collection of the systems of different energies at some particular temperature T is the canonical ensemble. In the previous example, we considered that the system has only one conformation phi, but it can have multiple conformation with the same energy, and this number of conformation is given by omega of E. Therefore, the probability of having energy E of this system is given by this Boltzmann distribution, and it is multiplied by the total number of configuration, right? And therefore the partition function G have also modified to this equation, okay? And it ensures that if we sum this P of phi over all the configuration, it should give 1, okay? Here we can use the Boltzmann equation to get the entropic contribution, right? Now you can see the exponent contains epsilon as well as the entropy, and we can express this quantity, that means E minus Ts, by single quantity A, and it is actually the free energy. In the previous slide we have shown how we can get the Boltzmann distribution for a system at temperature T. Now the same thing can be obtained by using the principle of maximization of entropy, where we consider that the system has different energy state, and the ith state has the energy E subscript I, and its probability is given by P of EI. And for such system, the entropy can be defined by this equation. And similarly, we can define the average energy, which is given by the summation over EI with its probability, and then there is the normalization condition. Therefore, we have to maximize this entropy by taking into account these two constraints, and it is actually expressed in terms of this single function. Here alpha and beta is the Lagrange multipliers. Do the derivative of j with respect to pi, then get the equation for this multipliers, find the multipliers, put it back and get the probability, and you can find, of course, the Boltzmann distribution. Thank you so much for watching this video.